Hello friends, we were discussing constitutive analysis. So, continuing with that, we have already discussed the phenomenological model, okay, and in that we have discussed the creep as well as high standard deformation, okay. So, Johnson Cook model in that, and then we have discussed for hot working Arrhenius type of sine hyperbolic relationship between stress and strain rate, okay. So, these are a couple of models which comes under phenomenological model, okay, used extensively, though they have empirical nature, but it is easy to kind of fit all the parameters, okay, and get some constitutive equation which can be used easily in any modeling work, okay, or to predict stress at any other temperature and strain rate, okay. So, we will now discuss this physical based model, okay. Again I am not discussing, again you can see if you go to any review paper there are tens of models, okay, but I am just giving you a flavor of what type of modeling is done when you are basing it on the physical phenomena, okay. So, in this first is this ZA model, okay, Zarelli-Armstrong model, okay, and this model is based on dislocation mechanism, that how dislocation multiplication is taking place or dislocation recovery is taking place and so on, okay. So, as you can see now that we are directly relating our constitutive equation with the actual deformation mechanism, okay, which we were not doing earlier. So, this is based on dislocation mechanism, effect of strain hardening, strain rate hardening and thermal softening on the flow behavior is considered. So, from physical basis they have included all these three parameters, okay. This particular equation you can consider it for any high strain rate and relatively low temperature, okay. High strain rate, low temperature kind of condition, you can apply this particular model to develop constitutive equation, okay. Now, what it does is that actually the stress is calculated by considering two contribution to the stress, okay. So, one contribution is a thermal contribution, okay, and another contribution is a athermal contribution which does not depend on the temperature, okay. So, by doing these two or combining these two different effect of stress effect on the stress, okay, you are trying to find out the flow stress of the material, okay. Of course, then you have to develop these particular models and equations. So, you can see that the equation, these two equations are shown here, one for BCC material, another one for FCC material, and as we promised in the first lecture of constitutive equation that you will have more constants when you are dealing with physical models, okay. So, you can see here there are the number of constants have increased. So, you have from C0 to C5, which earlier we had only 2, 3, okay, and on top of that you have these exponents also, okay. So, C0, C1, C3, C4, C5 and some exponent here. Similarly, in the for FCC material you have C0, C2, C3, C4 and so on, okay. So, basically again you can see that it is bringing down the effect of strain hardening, okay, with a strain hardening exponent here, also the effect of strain rate, okay, effect of temperature, okay, and that is how they are able to predict that what will be the flow stress for a BCC material. Similarly, they have proposed another equation for FCC materials, where there is a slight change in the way they have introduced the strain component. It has a exponent, instead of exponent n, now it has a exponent of half, that is 0.5, okay, and it is already multiplied in the exponential term. Earlier it was as a separate term, okay, now it is a single term here with the temperature and strain rate, okay. So, these are the two equations developed for two different set of materials. So, C naught is basically the athermal term, which adds the influence of solute and grain boundary to the thermal stress term. Okay. So, this is our A thermal component which we were trying to see in the first equation. Okay. So, you have A thermal and thermal components. Now, of course, as for any other model equation, people have modified this Zarelli-Armstrong model also. So, what these modified ZA equations usually are trying to do is, actually the strain hardening exponent, if you see in the FCC material, they have kept it as a constant 0.5. So, half is written there, so it is 0.5. Okay. So, strain hardening exponent, they are changing with some variable n, that means it can have different values instead of only a constant value 0.5, which is proposed by this ZA model. So, this is to taken into account in a better way the dynamic recovery which is taking place during the deformation process. Okay. So, model considering the other model is that which consider dynamic recovery. Okay. So, it is concentrated more on the recovery part. Okay. So, basically what we are trying to do here is that the change in the dislocation density as a function of a strain, okay, is related with two terms here, u minus omega rho. U represent the strain hardening part, okay, and rho is the contribution through dynamic recovery. Okay. So, that is why it is in negative term, as recovery will take place, the dislocation density will decrease. So, the rate of dislocation density increase as a function of strain, this should have a negative influence on that. Okay. Now, if you integrate above equation, you get the rho terms in this form, okay, that how the rho will change as a function of strain. Okay. So, under a steady state, the rho dynamic recovery, okay, that how what will be the dislocation density is dependent only on these two terms u and omega, and stress can be given by an equation like this, okay, which is sigma squared drV. Okay. I will tell you all this, that what do we mean by sigma drV and so on. Okay. And it has a exponent of 0.5, okay, and there is a strain term in the exponential. Okay. So, by from physical based model, you can predict now that what will be the flow stress of the material if you know sigma drV and so on. Okay. So, this is the model based on dynamic recovery. Now, there are model which also consider dynamic recrystallization. Okay. In this what they are trying to do is they are trying to find out the fraction recrystallized. Okay. So, to find out the fraction recrystallized, they have some parameters here. So, the equation is like this, 1 minus exponential minus k d and alpha minus epsilon minus epsilon c upon epsilon p, okay, and epsilon is more than epsilon c. So, what is epsilon c? It is a critical strain for recrystallization, which we have already seen earlier. If you remember that we were, when we were discussing the dynamic recrystallization, we discussed about this particular term. Okay. So, this is your peak stress sigma p. Okay. So, obviously, the strain corresponding to that will be epsilon p, and the recrystallization will start at some point here, okay, and this we called as epsilon c, the critical strain to initiate recrystallization, okay, and obviously the stress associated with that is sigma c, okay. And so, basically the idea is that the strain should be more than the critical strain, then only the recrystallization will happen, okay, and then only you will be able to calculate the fraction recrystallized. Okay. So, some parameters are there k d and n d here, which depends on the deformation condition. Okay. So, if you see actually the recrystallization process, that how this equation has come, this equation has come from this kind of Avrami equation, okay, where it has a typical S shape of curve, okay, and this type of curve you will see in large number of processes, not only metallurgical processes, for example, growth in bacteria. Okay. So, if you are doing some culture of bacteria, Okay. So, there will be some incubation time, then the bacterial growth will increase suddenly, okay, and it will increase exponentially, and as the volume of whatever system you have, okay, the ingredients are getting exhausted, okay, then the population will again become saturated and it will start decreasing and become saturated. This kind of curve you will also see in the phase transformation, that phase there is a incubation time before the by the time which the nucleation takes place, okay. Then there is a sudden increase in the nucleation as well as growth. So, fraction of phase transformation increases, okay, fraction transform increases, and then as the amount of volume becoming smaller and smaller of the parent phase, okay. So, again the kinetics decrease, okay. So, it has a very typical this A shaped curve, okay, like this, initially increasing exponentially and then decreasing. And this kind of behavior can be nicely shown with an equation like this, 1 minus exponential minus k t to the power n. This bring out both this behavior very nicely, and it gives you the fraction either recrystallized or fraction transformed if you are doing a phase transformation. So, you can see that it has very nice similarity with this. The equation is shown in the very similar way, only the parameters which are used in exponential has to be different depending upon what is your process which you want to know. Okay. So, as you can see here, fraction recrystallize is shown in on y axis, x axis has time. Okay. So, as you increase the temperature, the recrystallization kinetics is increasing, it is starting at lower time and finishing also at lower time, and all the curves have this kind of S shaped curve. So, they have found out the fraction recrystallized from the idea of this Avrami type of equation. Okay. Then they also find out the same, that how the fraction recrystallized can be derived or can be calculated from the flow stress curve. Okay. So, here we will see how it is done by flow stress curve, and here also you will be able to see that what we were discussing in physical based model, that what do we mean by sigma DRV. Okay. So, there are two curves shown here, one is with a broad peak which you see for dynamic recrystallization. Okay. So, stress increases, then you get a hump, okay, and then you have this dynamic recrystallization. If dynamic recrystallization is not taking place, only dynamic recovery is taking place, the curve will go something like this. Okay. And the difference between the two is given by some delta sigma. Okay. The initiation of recrystallization is happening at epsilon c and corresponding stress is sigma c. Peak stress is at epsilon p and sigma p. Okay. And this sigma DRV is, you can say, is saturation stress, and what you are getting after dynamic recrystallization, you can say it is a steady state. Okay. So, from this also you can calculate the fraction recrystallized, which is shown here. Okay. So, what they are saying is that whatever stress is, so if I subtract sigma DRV minus the stress at a particular point, okay, and divided by sigma p minus sigma DRX. So, this is actually the total drop in the stress because of the recrystallization. Okay. So, sigma p minus sigma DRX is the drop because of the complete recrystallization in the material. Okay. Once it is recrystallized, it drops to that from sigma p. Okay. So, that is, you can say, is a total recrystallization. Sigma DRV minus sigma whatever sigma you are at it to find out the fraction recrystallized. Okay. That delta sigma is the amount of recrystallization which has happened. That is why the stress has come down from this sigma DRV level to delta sigma level. Okay. And at this point it will be the recrystallization will be complete. Okay. So, this ratio of sigma DRV minus sigma upon sigma p minus sigma DRX should give me the, that how much is the fraction recrystallized, because by that amount the stress will come down. Okay. Again we are talking about strain more than epsilon c. So, now you have friction recrystallized from two different ideas, okay, one from the stress strain curve, one from the Avrami type of kinetics, and if you combine these together, okay, if you combine this together, so both has giving you frictional recrystallize, then you will get an equation like this, sigma equal to sigma drV, okay, minus sigma p minus sigma drx, okay, this you are combining here, and which is multiplied by 1 minus exponential minus k d, the remaining term, and so on. Okay. So, they found out the friction recrystallized from two different ideas, okay, and then they equated it, and from there they found out the what will be the stress of the system at a particular point. Okay. So, this is a model, physical based model, which is considering dynamic recrystallization. Now, there are sometime as I told you, artificial neural network based models also. Okay. So, in ANN based model, okay, the advantage is that you do not have to know the material behavior or actual deformation mechanism a priori, okay, you do not need that. Also, I do not need to know that which model I should be using for this particular material. Okay. So, I do not have to postulate a model, I do not have to determine the parameters of the equation, because we are not talking about any equation here. Okay. What we are doing is we are inputting, for example, in our case I am putting input of, if it is a steady state condition, my strain will not come in picture. So, I am inputting the stress at different strain rate and temperature. Okay. So, strain rate and temperature is your input, okay, and the output is your flow stress. So, basically your ANN model will be trained with the data which you have initially, and what actually ANN does in between is it fits lot of polynomial equation to your data, okay, and from there it try to minimize the error, okay, so that it gets a curve, okay, which can be used to predict the flow stress of for any other condition. Okay. So, if the strain rate and temperature will be used to get the flow stress, and you can use ANN model for doing that. Okay. Right now, because ANN model is something which because there is no physics involved, we cannot discuss that in greater detail right now. Okay. But if you are familiar with ANN model and all these ideas of machine learning and so on, you should be able to collect lot of data, maybe from literature if you do not want to do experiments yourself. Okay, collect lot of data from the published literature, use that to train the model, okay, and then try to predict the flow stress for some other condition which you have not used to make the model. Okay, then you will be able to say with confidence, okay, your model is working. Okay. So, with this we have kind of completed the constitutive models based on phenomenological model, physical based model, and ANN model. Okay. We have used only few models to bring out the flavor of each of this category. Okay. And also we have tried to understand that why we want to develop constitutive equation. Okay. The idea is to know the material behavior, so that you can also design material accordingly, and to use this for doing any FEM based modeling or so for your actual industrial process. Okay. So, once you know all the parameters, all the constitutive equation parameter, you will be able to do that. Okay. So, thank you for your attention.